Okay, so I included along with the homework, if you see the table 8, table 8 in chapter 9, okay? And then I also included a copy of all the formulas that were even in the video yesterday, and all the bottom, the voltages and everything, so you don't even have to figure them out, okay? So you'll have those also. So let me start presenting. Okay. Now you also got a little tutorial on how to present for some people who haven't done it yet. All right, so we're starting out. The first few questions, I broke it down, but the last few, because I also ran out of time, but I figured this way here, the slideshow presentation wasn't humongous. I just didn't have it all, each question worked out. So we're going to start with question number 1. Okay, so it's a voltage drop of 2 number 12 solid uncoated THW conductors. Now remember, the insulation type doesn't matter for voltage drop calculations. That's only for your, pipe fill calculations where the insulation matters. What does matter is where it says uncoated. Okay, so because if it's coated copper, what they did is, if you remember back with the video, the reason why they had the coated copper, they put a covering of tin on it because with the old rubber insulation, the rubber reacted with the copper conductor, so it would like stick to it and make it really hard to break down, crack. So they, put the tin over it so it stopped the reaction between the copper and the rubber. So that's where they really don't make. You might come across tinned wire, but they don't really sell it anymore. Okay. Solid uncoated THW conductor, 150 feet long, okay, connecting to a 9.8 amp load and 115 volt power source. Okay, would be, so the voltage drops would be what? So the formula VD equals 2, because you have 2 conductors. Remember, for 3 phase, it's 1.732, which is the square root of 3 because you have 3 conductors. K, is the constant. Now, because it doesn't say what type of conductor this is, the material, whether it's copper or aluminum, if it doesn't say, you always assume copper. So it's 2 times K times the distance times the current divided by the circular mil area of the wire, and that you find in table 8. So you go to table 8 and you find the circular mil area, number 12 is 6530. Okay, so it's going to be 2 times 12.9 times 150 times 9.8 divided by 6530 circular mils. So if you solve that, you get 37,926 divided by 6530. Okay, and that equals a 5.8 volt voltage drop. But the permissible voltage drop for 115 volts is 3.45. So you could see there you wouldn't be able to, use it. The voltage drop is too high, so you have to increase the size wire. Another voltage drop question, a voltage drop on a branch circuit. Okay, so because it says branch circuit, it's 3 volts. If it said, the service and branch circuit, then you would do 5% voltage drop, right? Because you're allowed 5% on the whole system from the, from the electrical meter down to the last outlet the circuit. All right. That's if you have a sub panel, sub feeder, or feeder going to a sub panel. See, they took away that word sub feeder. That's why I changed it. Just a feeder. Anything's a feeder now. There's no sub feeders and sub feeders. They're just feeders going from the main panel to the sub panel. And then it could go from another sub panel to another sub panel. So that's why they just call them feeders now. So voltage drop is equal to 2 times K times D times I divided by circular mils. All right. Excuse my yawning. You go to table 8 and you look for, number 8 wire. It's 16,510 circular mils, 16,500 circular mils. All right. So if you take it first and multiply 2 times 12.9 times 175 times 11, you get 49,665 divided by the 16,510 circular mils, and you get 3.1 volts of voltage drop. And the permissible voltage drop for 208 is 6.24 volts, because that's 3% of the 208. So, you're good. Next, now you're looking for what size conductor. You're looking for the conductor size. Is required for a 208 volt 3-phase branch circuit that has a 15 amp load 180 feet from the source. Now we're looking for circular mils, the wire size. Now, because it's 3-phase, you need to do this, use the square root of 3, which is 1.732 times K times D times I divided by the permissible voltage drop. Okay, and the permissible voltage drop for 208 is 6.24. All right, here we have, so we plug in the values, 1.732 times 12.9. Again, it doesn't say that it's copper or aluminum, so you assume copper, times 180 times 15. Multiply those out, you get 60,326 divided by 6.24, and you get 9,666 circular mils, which when you look at table 8 has for number 12, it's 6530, and you have to go up to number 10, which is 10,380 circular mils. You always go up a size, never go down. So this is more or less, this is what I want to see on your paper. I want to see, the formula, okay, and then the values plugged in, solved, and then the answer. And you can either circle it or highlight it a different color. And what's nice about once you write the formulas once, you could just take it and copy them and paste them and then fill in the values. Okay. How far from a single phase 240 volt source can you install number 10 DHW stranded copper conductors if the load is 16 amps on the branch circuit? Again, you want the 3%. Okay. Excuse me. Pause this a second. Okay. Okay, so you plug in the values into the formula. Whoops, I tapped it. So it's 10,380 times 7.2 divided by 2 times 12.9 times 16, which is 74,736 divided by 412.8. And then that gives you a distance of 181 feet. Remember, we could round up to the whole number. Now we're looking for current. What is the maximum load? Okay. Permitted on a 115 volt single phase. So, using the 2, not the square root of 3, because it's single phase. All right. For number 12 THW stranded conductor. Again, it doesn't say copper aluminum. You assume copper. 150 feet from the source. Okay. So you can see now I said I stopped, breaking it up. I'm just putting it out. You have the idea now. Okay. So it's current is equal to circular mils times the permissible voltage drop divided by 2 times K times D. So if you see from the last one, the distance formula, the I and the D just swapped. Okay. So you're going to get the circular mil for number 12 is 6530. See, some of these you're going to start remembering the circular mil value because when you start working with it a lot. Times the permissible voltage drop for 115 volts is 3.45 divided by 2 times 12.9 times 150, and that comes out to be 22,529 divided by 3,870, and that gives you 5.82 amps. That's the maximum current that you could draw on that branch circuit without causing to exceed the permissible voltage drop. Okay, number 6, what size conductor? So you're looking for circular mils again, right? All right, and this is single phase. What size conductor for a single phase, 1.5 horsepower, 230 volt motor with a full load current of 10 amps, 150 feet from the source. So again, you're looking for circular mils. The formula is 2 times K times D times I divided by the permissible voltage drop. That's what PER means, permissible. All right. So it's going to be 2 times 12.9 times 150 times 10 divided by 6.9. So it comes out to be 38,700 divided by 6.9, and that gives you 5,609 circular mils. And we know that number 12 is 6530 circular mils. So you go with the number 12, because number 14 is only 4,110 circular mils. So you have to go up to the next size. So also, because I can't see the screen, that's why I'm going to be starting to set up. I'm going to get another screen for my computer so I could see it. But if anybody has any questions, you could just unmute your computer and ask the question. And if you can't unmute your computer, just pose a question. Everybody else can watch the chat box and let me know if there's a question, or I could answer it when the presentation's done. And I could always go back to the specific slide. It's not a problem. Okay. So does anybody have any questions thus far? Kind of getting it, seeing how to use the formulas. Maybe a little different from the video yesterday. All right, so here you're looking for the permissible voltage drop. And again, it's single phase, so it's 2 times K times D times I divided by circular mils. So it's 2 times 21.2, because now we're talking about aluminum. That's what the AL is for. Okay, so the K is 21.2 times 175 feet times 11 amps. Okay, divided by 16,500. That's the circular mils of number 8. So it comes out to be 81,620 divided by 16,500 gives you a voltage drop of 4.9 volts, which the permissible voltage drop for 208 is 6.24. So you're good. Number 8, when sizing conductors for feeders and branch circuits, the NEC blank that we take voltage drop into consideration. It requires you. Okay. those are the two words, requires or permits. Okay. Required is a code you must do. Permits means it's okay, where like when they use the word shall, I mean, shall or shall not, it means it's required. If the code says may or may not, okay, then it means it permits it. It means you could do it or you don't have to. Okay. But when it says it shall, when it uses the word shall or shall not, it's required. Okay, number 9. What is a voltage drop? It's kind of similar to question number 1. It just changed around, the amperage and the distance. All right. So voltage drop, it's 2 times K times D times I divided by the circular mils. So if you multiply 2 times 12.9 times 100 times 12, that equals 30,960 divided by the circle mil area of number 12, which is 6530. And that gives you a voltage drop of 4.74, which is too much because you're only allowed 3.45 volts of voltage drop. So you'd have to go up to the next size conductor. You could see why now when we talk about like when you're working in homes, like when you're running wires in home or business, that's why we usually use 70 feet, as once you go over 70 feet, you want to take and usually go up to the next size conductors. Number 10, you have a single phase 5 horsepower motor. Okay, so right now we're giving you what the full load current is, more towards next year. Well, next year when you're doing motors and motor control, Mr. Ash, you're actually going to learn how to look up to do the load. When you're doing the load calculation for motors, you're going to look it up in table 430, 43248. Table 43248 for single phase motors. Okay, and 43250 is for 3-phase motors. Okay, but here we're giving you it so you don't have to worry about looking it up. So I want to know what size wire. Okay, because when it says apply the recommended voltage drop limits, so we know that what is the permissible voltage drop for 115 volts, it's 3%, which is a 3.45. So circular mils is equal to 2 times K times D times I divided by the permissible voltage drop, which we said was 3.45. So then you take it and multiply 2 times 12.9 times 110 times 52, and you get 147,576 divided by the permissible voltage drop at 3.45, and that gives you 42,776 circular mils. And if you look that up in table 8, number 4 is 41,740. So you have to go up to the next size, which is number 3, which is 52,620 circular mils. So, any questions?